we don't need the transcription. Okay. It's recording. All right, we have quite a few things to go through today, so I hope you'll be with me. We will probably have a short break in the middle. I don't know how long it will take. Hopefully, in two hours. Hopefully, not too much over, but we'll see. Any questions before we start? No. Put on the slides. And record screen. Let's see. Okay, share screen. Can anybody give me a wave if you can see the slides? Great. Thank you. Thank you. Thank you. Feel free to put it off. All right. Now, for the past few weeks, if you have been up to progress for this course, the learning items or the core data objects for this course, which is arrays and data frames, including series. You know that series and data frames they are, I guess, two sides of the same coin. And today we're going to review those critical points of the data objects. We will touch on lists slightly, which is the content of even more previously. Sometimes we use lists and these more basic data objects to define our series and data frames, because it's convenient and it works well.
Professor, you muted yourself.
Very interesting. I guess that's the new setting. Well, how much was lost? Oh, I see. But how much did you miss?
I think the whole thing.
Sentences.
So did you hear me talk about the main contents these 2 weeks?
Yes.
Okay, so I was just muted as I turned the slides. That was a relief. Great. So a few reminders. Hackshop 3 will be due at least end of today. If you can turn in, at the end of the class, it will be better. There's no need to rush, but if you wonder, then you don't have to wait until the end of the day. Feel free to submit when you're done by the end of the class, but it's okay to go over time for sure. There's no reason to rush. And homework 2 is due by the end of the week before Sunday. Today, let's see, I do have another side of the slides, getting a little bit confusing. This is also slides as well. So we'll go through lecture slides, and then we'll do the Hackshop 3 and also talk about a few points about the homework 2. But for Hackshop 3, I will talk about each of the question. But before I talk about each of the question, I highlight a few key points as part of the lecture. So that was that. So that's going to be the first content here. All right. We'll start with arrays, and then data frames. They share the same core because NumPy is the core kernel behind data frames or behind pandas package. But then pandas add very useful things on top of arrays and also simplify things in other aspects. So going forward, data frames and series will be more used, but never forget about arrays because we use them occasionally from time to time. I will present their differences, similarities, but most importantly, differences, and then how to deal with different scenarios. All right, so that's the goals for today. Here now, by this point, you have completed learning module 3. I think 3.1 and 0.2. 3.1 is about arrays. 3.2 or NumPy in general, and 3.2 is about data frames and series. And going forward, module 4 will be about data manipulations, mostly dealing with series and data frames. So it's sort of performing more advanced, more complex maneuvers with data operations. So that would be the interesting parts of data science. Today is the more fundamental sides of data science. We're talking about Python analytics. Okay, so arrays are multi-dimensional data objects that are highly regulated. So the format, the shape of it is highly symmetric, normal in a way that cannot have different sizes across different elements of a dimension. And here is what I mean. So 2D, 3D, let's do this. Now with 2D, 1D, it's easy to understand. 1D is a vector. Sort of like it's like list. It's one dimensional. It only has length. There's no other dimension. Think of it as a line of dots. That's one dimensional. A line that only has left and right, or up and down, but no, not both directions, right? And then for 2D, we are talking about the plane. Lines that are lined together. In the sense of, let's see, make some joins here. So I think it's fairly straightforward. So let me not talk too much here. If one dimensional object is dots lined together, then 2D is a few lines or a few rows stacked together. But the regulated property here means that you cannot have different lengths across the different rows. If one line or one row has 4 items or 4 columns, then the second row must have 4 columns as well. And then don't forget the outer brackets. 3D, meaning a bunch of 2Ds stacked together. Think of it as a cube. If the surface is like rows and columns, you have rows and then columns, that's a surface. Then that's the one slice. one plane, then the 3D data object is like a bunch of slices stacked together. The regulator property also applies here. You can only have the same size throughout. You can have missing values, of course. So this is missing value, but missing value does not mean it's empty, or it does not mean missing value is like empty, but it doesn't mean that it doesn't take memory. It still takes memory. There's a placeholder over there. So the structure should be regular and symmetric, or consistent. And going to more higher dimensional, it's less intuitive. Think of 4D as a cube that transitions throughout time. So time would be the fourth. Okay, somehow I can't write here. So time. This data object might change shapes. If you cut off one portion of it, it becomes smaller. So, no, wait a minute. In terms of the 4D object, you cannot have different shapes. It has to be consistent. So the same 3D size has to be the same across time, but the values can be replaced. The elements of these of the data object, the array, the values can be replaced with different values. There you see the transitions across time. So that reflects the fourth dimension. With higher dimensions, it's harder and harder to talk about. But that's not the scope of the course. Anyway, here mostly we are going to expect you to understand up to 2 dimensions, maybe 3, in terms of arrays, but we'll focus more on data frames. So data frames is up to 2D maximum. So, that removes a lot of the complexity here. In computer science, they will talk about higher dimensionals because that's going to be useful. All right. Now let's zoom into arrays. In NumPy arrays, the key to understand it or use it without making mistakes, use it without invoking errors in Python is to understand how to understand the dimensions and structures and the notations of it. By notations, I mean indexing and slicing. So differentiate between these two forms. One is this format. When you have the name of the array, the data object, the object name, or the instance, this array instance is named ARR1, array1. When you have that and followed by brackets, you are trying to index. You're indexing the values or slicing the portions of this array. In this case, when you're indexing, you use comma to differentiate different axes or different indexes. Okay, different levels of indexes. So let's say index level. The very first one is always referring to index. It's not index 0, but it's not index position 0, but index level 0. And in this level, there are different positions beginning from 0 to 1, etc. So sometimes to make it clear, sometimes we also call it axis. This is the first axis. It's like x and y, 2 dimensions in a scalar plot. 0 axis, we have axis 1 or index level 1, index level 2, and so on and so forth. So in this case, this array has many dimensions. One index level is one dimension. So it has 1, 2, 3, 4, 5, 6, assuming this is 1, and then 7. It has 7 dimensions. It's a high dimensional array. It's very complex. It's hard to visualize, but this is just for an example. So when you are using the indexing or slicing notation, this is the way you do it. But alternatively, a lot of times you'll see something like that. You'll see square bracket, and then you have value 1, 7, a bunch of random numbers, 2, -4, 8. All right. So sometimes you see comma when you call it. Sometimes you don't. But when you don't see comma, then assuming these are separated. These are separate numbers. So what does this mean? When you see that, without the array name before it, now this represents one array or an array instance. This is not trying to index the values of an array, but this represents the content of an array. To determine the dimension of an array instance, you focus on the levels of the square brackets. If you only see one level, meaning one pair of square brackets, that means this is a one-dimensional array. There's only one dimension. You call it a vector or one-dimensional array. It has 5 elements. And now, so let's give this a name. This is, let's say this is array 2. That's one-dimensional array. Now I write array 2 with square brackets. And now I'm trying to access the items or the elements of this array. This is using indexing notation like this. And since this array 2, is only one-dimensional, I cannot have comma here. It would be wrong because using comma indicates that there are at least 2 dimensions. I'm trying to access 2 index levels, right? But not. This only has 1 dimension. So I should not use the comma. And here, using index position, if I put index 2 in this first or 0 axis or index level 0, which item am I trying to access? By this point, you know that the index positions always begin with 0 in Python. So array 2, try to index position number 2 is which item or is which element?
2.
2.
2.
Third
Yes.
element, which is 2.
Right. So index position, this is the position. This is position 0, 1, and 2. It's trying to index that one. And if you use slicing, array 2, 1, slice 2, 4. It is trying to slice 3 values. And I think we talked about in this class, I believe it's in this class, we talked about how to determine quickly by following a formula, how to determine the number of elements that's returned by using range notation or the range function or slicing notation. That's going to be the same, right? Similar by the same logic. You take the difference and then divide it by the step, and then you take the ceiling, you round up. So here, the step is 1, so you get 3 elements beginning with position 1. So you get slice of the array 7, 2, -4. All right, hope that's clear. So don't be confused when you see square brackets and carefully determine which case it is you're looking. Are you looking at a slicing or indexing notation, or are you looking at an instance of NumPy arrays? A few more words. Determining the dimension of an array solely depends on the levels of the square brackets. So with one dimensional array, you see one pair of brackets. What if you see something like this? 0, 1, 2. I'm running out of space here. 3. That's bad. Let's see. Let me restart. Okay, let me use this here. If I have, hang on. Anyway, let me do it here. So if I do like this, 0, 1, 2, 3, 4, 5. How many dimensions are there? I hear 1.
Yes.
Any different opinions? There's only 1. It's written in 2 lines just because I'm running out of space, right? And in printing format, sometimes this happens when the row is too long. It has to be cut off, but it doesn't mean there are 2 rows. So the key is to focus on the levels of brackets. But however, if you have something like this, how many dimensions?
2.
2 dimensions, because you see 2 levels. 2 levels every time, or the deepest level is 2. So hopefully this is hopefully this is clear. What if you have something like this? How many dimensions?
Each is 1 dimension.
Exactly, there are 2 arrays, right? Very good job. There are 2 arrays. This is not one array, and each array has 1 dimension. Great. All right, I think this is clear, and it's time for me to flip page. Okay. Now, let's see. So, time for me to make some demo. So that's the agenda. First of all, to refresh your minds, there are a few tricks for making lists or sequences, like lists, a list of sequences, sequential numbers. Can you hear my slideshow? Can you see my slideshow?
Yes.
Okay.
Yes,
great.
we can see it.
Can you see it?
Yes.
Yeah, you see demo list 1, right?
Yes.
Okay, great. Now, to quickly make a sequence of numbers beginning with from 0 and however long you want to be with steps 1, this is how you make it. You will need the list function though to turn the range object into a list. All right, let me run it. To quickly get a sequence of not numbers, letters. Excuse me. To get a sequence of letters, you can get this, and then you can use the string ASCII uppercase or lowercase, and then you can do slicing. Get the first 10. That's how you can get it. to get a list of sequences that starts from an arbitrary value, you can define your range function slightly different with the beginner, with the beginning number, with the different start. You can get that. So that's very quick. Now, with NumPys and pandas, we're going to use with arrays and data frames, we're going to use NumPys and pandas. Run this. Okay, so what's the question? How to make this array quickly? Now observe the dimensions. How many dimensions and what are the dimensions? We can describe by something, you know, 1 by 2 or 3 by 4, 1 by 2 by 3.
1 by 3?
Say it again. I heard 1 by 3.
Yeah, I said it.
So
3 by 5.
3 by 5. So 2 dimensions.
3 by
3
5.
by 5. 3 by 5 means there are 2 dimensions, right? If you were to slice it, then let's say this is air 1. If you try to slice it, then sorry, this is bracket. Then if you want to specify both the rows and columns, you have a comma in between, and then level 0 and level 1. And the size of this level is 3. The size of this level is 5. 5 columns, 3 rows, 3 by 5. All right, are we clear? Now, how to quickly make it in Python? Here is what I would do. So we're going to leverage the NumPy A range, which is very similar to range function, but the difference is that with NumPy A range, it returns an array, whereas range function returns a range object. You would have to turn it to array in addition. So A range skips that or integrates that step into one function. Now, I need to specify the total sizes of the data object. There are 2 ways to do that, or multiple ways to do that. One way is to calculate mentally, and then specify how many objects. It is 3 by 5, so it is 15. Or you can, you can call the function of a simple multiplication function, call it directly on the fly, and then without having to calculate the total number to make sure it's always right. This is going to be always right. Now with that, you are going to get an array of 1 dimension. So let's just show that. If I do that, you're going to get an array of 1 dimension from 0 to 14. What we need is to make it a 3 by 5. So like you learned in the modules, we're going to use Reshape to make it 3 rows and 5 columns. Now it does not really matter if you put them in another level of brackets or parentheses. It works the same, and we can check. So, the levels of tuples here, it does not really matter. So doing this way, we get the same, and we can even put 1 more level, 1 more tuple here. It gets the same. Essentially, it will be ignored. All right, so that's the same. Clear this one. So that is how you quickly get array 1. So then we'll use this array as a motivating example to do a few practices. Something I should also mention that the 2 axes, right here, it's two-dimensional. So there are two axes or two index levels. The axis 0 or level 0 always comes the first. It's on the left, right? It's on the left. And axis 1, here it's the bottom. It's always on the right. So the order is important. It goes the same with when you try to index. You know, if you try to index with the comma, you're accessing the two axes or two index levels. This is always the axis 0, which is a higher level dimension. And then the axes on the right are always on the bottom. The bottom, the most bottom dimension is always the columns or the elements in the row. So, and when an array, when a two-dimensional array, when the values are being placed into the array, it's always, by default, it's always the bottom axis, the column in this case, or the column in any case. The bottom axis gets flipped the most quickly, which leads to the values filling rows by rows, because it stays on the same row, but it changes the positions of the columns more quickly. So the first row gets filled and then goes to the next row and so on and so forth. We'll see that more clearly in a few moments. All right. Try to index the two-dimensional arrays. Involves a few tricks, and you have learned about these in the modules. And I'm only here to highlight a few key points here. So if I only specify one axis, what does it mean? Am I trying to slice or index a row or column?
A row.
A row. Yes, a row. Row is in the two-dimensional array, it's the topmost dimension. So it's a vector of elements, right? So and also the levels of brackets makes it very clear. Let me do this. Let me print it to make it more clear by removing the comma. This is index position 1. It's the second row, but whichever row are you looking at, it is one kind of, it's a one whole row. So, and there are 5 elements in each row. So row here is a higher level dimension, and the columns or the elements of each row represents a lower level dimension. So that's right. If I do this with a single pair of brackets, it's going to break down the dimension. Original dimensions there are 2 levels of dimensions, 2 dimensions. With one pair of brackets, I'm going to extract one particular row and drop the higher level dimension. So this is what's going to happen. The returned array is only one-dimensional, but there's a way to retain the higher level dimension if you want. So what if I want to return a 2-dimensional object, but only with one element in the higher level, which means it's a 2-dimensional object with only one row. Does that make sense? I can have a two-dimensional object with only one row. So, and when I need, I can add more rows. So it's still a two-dimensional object, but only with one row. In order to do that, you would need to use, we need to use two levels of brackets. This time, let's get the same row. By using double layers, you are preserving the dimensions here. And this becomes useful, not in the sense of arrays, but it becomes useful in when you're dealing with data frames and try to manage the data sets in the way that you want. Sometimes you don't want to get a series, you want to get a data frame, but only with one column. Then you can add columns very easily. With index, with series, you cannot add one more column because it becomes data frame. So this is just a precursor of the technique. And when we talk about data frames, we'll use the same technique. When it comes to indexing, two dimensions here, you would put different numbers. So if I put 1 and 1, which element am I going to get?
Six.
6, exactly. Now let's confirm. And in this case, if it's getting only one item, it's going to be a scalar. There's no dimensions here. It's just one single item, 1 point, right? Different from, even though it's one layer of brackets, different from that because that's getting a row. It must have at least one dimension. Okay, what if I use a slice? 1, 2, 3. Since I'm slicing over multiple rows, at least I should have one dimension. Depending on the number of elements that are indexed or sliced on the other dimension, the returned, the output, the dimensions of the output will be what would depend. In this case, you know, you would expect that it's the column index position 1, but I'm slicing 2 items, so it's going to be one-dimensional, right? And then, of course, I can do slicing on both directions, and in that case, I should expect a 2-dimensional item. All of these should make sense, pretty straightforward. But let's change the game and then see what will happen in this case. So if I do a 1 and 3 on the rows, which means I don't want the index position. There's no 3. Sorry, there's only up to 2. Excuse me. So because there are only 3 rows, because I want to skip the row position number 1, I use a list notation, and then on the columns I use the same slicing notation. Is this still going to be straightforward slicing or fancy slicing? Or fancy indexing, I should say. So if it's straightforward slicing or indexing, then I would expect 2 items by 4 items. I should get 8 items, or 8 items in a 2-dimensional format. Let's take a look. That is right. So whenever you have slicing in either dimension or both dimensions, you get straightforward indexing or slicing. It's the first row and the third row with these data objects, beginning with index 1 and all the way to the end. Okay, but if you say, I want to pick and choose on both directions, this is going to cross into the fancy indexing territory, and the game is completely changed. So think about what you would expect, and I'll run this and show you what you will actually get. Now it looks straightforward. It's the 0 line row index 0 and 2, and the columns 1 and 5. There's no 5, unfortunately, so let's change it to 2. So column position 1 and column position 2. So I should get 1, 4. Excuse the footsteps. That would be my son trying to show how sporty he is, I think. But anyway, so all right, row 0, column 1, this number, and row 0, column number 4, or column position number 4 is 4, 1, 4, 11, 14. I should expect 4 elements by indexing the rows and columns positions. But what a surprise you get. So without using slicing, it suddenly changes to fancy indexing, which essentially it does not sweep, it does not slice, across the rows and columns, only pick and choose. So it's picking 2 points based on 0, 1 position, which is 1, and then 2, 4 position, which is 14. I only get 2. And even though the 2 numbers are on different dimensions, they are on different rows and different columns, you get only a one-dimensional array. So the structure is flattened. So fancy indexing is rarely used because it's less intuitive. It doesn't have wide use cases. So avoid picking and choosing different rows and different columns. Use slicing at least in one place, right? That would be for arrays. Okay, any questions? A few more use cases for arrays. Now I make this interesting 2-dimensional array. How do you make it? I start from a sequences, so 0 all the way to 15, 0 all the way to 15, which is 16 numbers, but I'm using broadcasting by, I think there's a hand. Is there a hand? Manal?
Professor, yes, Professor, can you zoom in a little?
Oh, it's too small. Sorry.
No, thank you.
Okay, I hope this is better.
Thank you.
Sure. If you can unmute yourself and talk about your question, that would be better. Because I'm sharing the whole desktop. It'll be harder for me to look at the chats at the same time. Just in case. So here I'm going to talk about this, what I did here. So I have a natural sequence, but I would like to have gaps between the rows, but no gaps between the columns of each row. So 0, 1, 2, 3, 10, 11, 12, 13, 20, 21, 22, 23. What I did is to add different numbers across the different rows, but the same number is added to all the columns of the same row. This is broadcasting. With broadcasting is also covered in the tutorials, although with less examples. So here's one. So when I have a 4x4 array, and then I make one array, right? And then I reshape. I specifically want 4 rows and 1 column. Without reshaping, it's going to be a row basically. So with that, it's going to add the same value to the same columns, but then the columns have gaps. I want the rows to have gaps, not columns. So I specifically call it to reshape to have 4 rows and 1 column. And in this case, it's going to fit that column to each of the column as long as the length of the columns match. In this case, it matches. 4 elements matches the 4 rows of each column. So I add that column to each of the columns. It ends up adding the same values on the same rows, but different values on the different columns. So I get this nice, interesting array. And with that, let's do some slicing exercises. Recall that if you use slicing, it's going to give you, if you use slicing on both of the dimensions, you'll get a 2-dimensional array, right? So 2x4, not 2x4, sorry, 2 to 4 on the rows and up to 2 on the columns. I will get 2 times 2 is 4 items, 2x2 array. This is what it looks like from the previous page. If I use this notation, it switches to fancy indexing. I'm only going to get 2 elements and also flattened in 1-dimensional array. So that's what you would expect. And one more, if I specify 2 elements on the rows and 3 elements on the columns, guess what you're going to get? It's not going to run. And let me show you, but let me make sure this is run. I need to run it. Did I run it? Maybe. But anyway. So run this. It's the same. Okay. So with this, if I run it, it's going to give me an error. It won't work because the number of elements mismatch. This is not slicing. This is fancy indexing. You must have matched number of elements on both directions, on both axes. With the letters, with an array of letters, the same way. Let me run this. Okay, slicing by this, I get 2 rows and 3 columns. That's what you get. And then the same array, if I do fancy indexing with 3 elements on each index, on each index level, I will get an error because there are no index position 6. It's only up to 5. So if you run this, you're going to get an error. Let's try that. 6 is out of range. So you would have to modify by up to 5, and then you will get 3 elements flattened in a 1-dimensional array. So that would be all for the arrays. Any questions? Right, then we'll transition. Question?
I have a question. Yeah,
Yes.
just overall, before we transition, like, what would you say? It kind of makes sense, but what would you say is the main difference between the array and the data frame?
The arrays and data frame? I'm
Yes.
going to talk about that next.
Okay, thank you.
Right. So, I mean, they are different objects. You know, they are defined somewhat differently, but those are more technical. And what we're going to focus on is indexing and slicing, the differences and similarities between indexing different parts of the array versus data frame, and then slicing different areas or different components of the arrays versus data frames. That's what we're going to focus, okay? Because we're focused on practices. So arrays versus data frames, there are a few similarities, but they are quite different. Now, this array 1 is from previously, and that's the same. It's a two-dimensional array. We're going to make a data frame based on this array. So in this sense, you can see the commonality between them, at least on the data object level, because array is from NumPy, data frame is from pandas, and NumPy is the number core of pandas. Okay, so here, quickly making, well, since we have arrays, do you still remember how to make array 1 very quickly? NumPy arrange. Follow along with me if you want. That is good practice. NumPy array, I have 3 by 5 elements is 15, and I want to reshape into 3 rows and 5 columns, and that would be it. Okay, so with that one, I can quickly make a data frame by using pandas as a data frame without specifying rows and column indexes. In that case, I'm going to use the default values or default customs for and let the program define the column labels and row indexes. So if I call it, you'll get a nicely formatted or nicely displayed data frame with the metadata, which means the index values, or the index values and the column labels, bold for you, and then out of the main content area. You can alternatively do display, which is going to give me the same thing, calling it calls the display function by default inside Jupyter Notebook. So that's a very good, that's IPython utility here. But if you were to print, you're going to get slightly different format by stripping away those bold and some, because this is printing. On printing, it also keeps the, it uses what's called the fixed width font, right? These are fixed width font. They are aligned very nicely, but it doesn't have that table format. It's only lined up very well. All right, so keep in mind the differences. I'm going to, for the most part, I'm going to stick with the display format because it looks nice. Okay, now slicing. Slicing for data frames and series almost always use .lock and .ilock, or use .lock or .ilock, but not use bare squares. There are use cases where you only use bare squares. I'll talk about it, but in typical indexing and slicing, you use .lock and .ilock. And keep in mind, these are square brackets. So the only difference between data frame best practices and including series, data frames and series best practices versus arrays. This is array here, I'm running out of space. Okay. The difference is that you use lock and ilock for data frame for Panda objects, but for arrays you use bare square brackets. But in both cases you use square brackets. Okay, don't use regular parentheses. That would be no, you'll get an error. So, you know, and then let's do some practices. With these, you get view versus a copy, which means with these, with ilock and lock, lock means location. With ilock or lock, slicing or indexing, you can replace values of the original data frame or series. So a few practices here. Now, to slice, let's see, df1 dot, let's say ilock, right? It's ilock, and lock. The difference is I means using index. So ilock means to use index to get the location, versus bare lock, just lock, means to use labels or the names of the index to index or slice. That's the difference. So with ilock, you would expect the behavior to be exactly the same with arrays, right? So treat ilock as if it's indexing or slicing an array. So in this case, if I do ilock1 for data frame 1, df1, what am I going to get? If it's slicing, if it's indexing slicing for arrays, then you would expect
get
that
the
it
row.
will get one row, yes, and the row with
The
position
second row?
1. Yeah, the row with the second row. And then how many dimensions will you get?
Just
It
one.
strips one level, right? And then you only get one-dimensional object. And in this case, it's not an array anymore, so I guess that's the only difference. The behavior of the slicing is the same, but the output would be a series here. Now this looks bizarre. What is this? I get two columns. No, you get one you get one series. This is one-dimensional. It always prints as if it's a column, but it doesn't have to be a column. It's just one-dimensional, right? It lines up like that because it has to display the index positions of this series. So that's the difference between series and one-dimensional arrays. Is the metadata. The metadata, the exact index, and these are not these are not necessarily the index positions, because you can change this. If you have studied well the series as well as data frames, you can change the indexes of the series to be not regular, you know. So that's why this is important. You cannot assume the first item only has always have the index label. These are the labels. The position always don't change. So, you know, with this one, I can use another level of ilock, right? So I'm using indexing on this series, and if I do 3, it's going to index the element with the position 3, which is 8. So I will expect to get 8, right? And as a scalar. So, okay, the difference here with lock. This example is going to show you the difference between lock and ilock in terms of the series. Once I get this series, I use lock. Lock means to use index labels, right? With the previous example, I use ilock, and position number 3, I get element 8. However, let me copy and make sure that you can see the contents of this one. Let's see. Okay. So this is, make it a markdown, df1.ilock1. What I get is this. Nope, this won't work. Okay, sorry. This has to be indented, right? Let me reduce a little bit. So hopefully you can still see it. So df1.ilock1 gets one row, and then it's displayed at this. If I use ilock, then I get item position 3, which is the 4th element. I get 8. However, if I use .lock with the same number, 3, and guess what? I'm not going to get the 4th element. Well, in this case, yes, I will. Sorry. Let me do some trick here. If I, let's see. So the point is, the index position and the index label are not always the same. So that's what I'm trying to do. Well, maybe the next example is going to make it more clear. But other than that, so just know that the ilock behavior is very similar to the arrays indexing and slicing. But the lock is quite new to DataFrame, and in some cases, like in this case, the ilock and lock will return the same element, but not always. That is because of the metadata. The index labels and as well as the column labels can change. You can change it, which will change the behavior, or which will change the actual content returned by using lock, and will make them different. So next example, let's see. In a few examples, I will show that the two will return different things. Okay. Now, so with let's dig deeper into data frames and series. One property of the data frames and series is that the indexes and the column labels, they are both indexes. They are just called differently because we use columns and rows to as the convention to refer to the two levels of indexes. Both indexes, the columns and the index, both labels, you can change them, but they enforce when you try to refer to them. So given df1, this is a df1, on both the column labels and the row indexes, they are all numbers. What if I do this? What if I use the content of df1? That's what df1 looks like. If I use the content of df1 and define another data frame, df2, and then I seem to be defining the new data frame. For the new data frame, the columns should be A, B, C, D, E that matches 5 columns instead of 0 to 4. And then I define the indexes, the index labels, to be 10, 11, 12 instead of 0, 1, and 2. I'm expecting to get the same array values, but with different metadata. All right, that's what I expect. However, when you run that, it's not going to give you the same thing. And, you know, you're going to get missing values across all. And the reason is when you define a new data frame by using an existing data frame, it does not only get the values, but also it gets the metadata. So that's why we say the indexes are strictly enforced. The index values, the metadata come along with the data frame when you use it. And unfortunately, the definition of data frames, the metadata parts of the data frame, although it looks like I'm defining new column labels and new row indexes, it is not actually redefining. It is actually using. So if you were to flip to, and this is what I suggest, when you are learning programming and in the future when you're using Python, you will most likely going to search. Let's use Google here. You're most likely going to rely on the documentation resources a lot. So search Google pandas data frame. I'm going to get the most current documentation resources for pandas. And on there, I'm going to be able to look at each of the objects and functions very quickly. So this is the definition page for data frame. Now, with the data frame, pandas a data frame, I can provide the data, I give the index and columns, and then specify the data types and so on and so forth. But if you look at, so the data can be data frame, it can be ND arrays, that's NumPy arrays, it can be a list, it can be a dictionary, or even data frame. And if you look at the index here, it says the index to use for the resulting frame. It's not the index to replace or to renew for the resulting data frame. So if the index values that I provide here, if the index values that I provide is included in the existing data frame, then it's going to select that. So, you know, if I change one of these, it's going to select that. But if it's not included in the existing data frame, it's going to return missing values because the index, the column, does not exist. The same goes with the index. So if I change it to 0 for the first row index, then let's see, should be labels. I should get, okay, no, even though the index values are correct, 0 is correct. I'm still not getting the first row because the columns are mismatched. So you would have to get both the index and the columns correct in order to get the correct value. So here is to demonstrate if I correct both places for the same value, I'm going to get this 0 here, but nothing else. So I'm going to have the column label as 0, but then the remaining as incorrect, B, C, D, E, there's none of them. For the index, the first row is correct. And with this, I'm expecting to get the first element out. So this is illustrating the strict enforcing of the metadata when you are reusing an existing data frame. And this goes with other maneuvers like, concatenating or appending or joining. It's the indexes are strictly enforced and compared. So keep in mind about that. You're probably going to make a few mistakes down the road unexpectedly. And when you see a bunch of missing values, where you expect something different, but you get missing values, chances are that the metadata doesn't match, and then you get a surprise. So carefully, even though you don't get an error here, I'm not getting an error, which is interesting, because there's no coding error per se, but the result is not what I expected. The reason is because of the mismatched metadata, right? So hopefully that makes sense. Any questions? The same goes with the series. Series and data frames are two sides of the same coin. All right, going deeper with the .lock and lock, both of these get a view, so you can replace it. So in a sense, if you say df1, wait, strike that. I should type .lock or .ilock. Lock, let's say the first row. If I slice it but put it on the left side of the equal sign, then this is getting assigned something else. And then if I assign something, a list or an array with the 5 elements, which means it will replace the entire row of this row being sliced. It's going to replace the values of the original data frame. So be careful with that. Typically, we will not put this slicing object on the left side unless you are manually replacing a particular value or particular row purposefully. Typically, we don't do that. Let's see. All right, this is just to repeat the point. Ilock is using index positions to index location, whereas .lock is using the labels. So let's do a few examples in the next. All right, so here, I'm defining this df4. It's a sequence of numbers, 12 elements, 4 by 3. The column labels are 1 or A, B, and C. The index names, the index labels are 1, 2, 3, 4. It begins with 1, and it is labels. It's not numbers, even though it looks like it's numbers. So sometimes if you are indexing with numbers and it clearly looks like numbers, but you get an error, that's because, the labels are of different data type. Carefully check that. In this case, it begins with 1. So in this case, the ilock and lock will give you different answers. Let's use ilock first. With df4, I use ilock to slice only the first dimension, which is the rows. I get all the columns of these rows. If I do 1 to 4, which rows do I get? And how many rows do I get? Anybody?
3.
First 3 rows.
3 rows with ilock, yes. Which rows?
Second,
Just say
third,
the
and
beginning
fourth.
number of the rows. 0 or 3 or 6 or 9.
369.
036. I think it would be
036 is
Yeah.
not the result.
369.
369 is the result because this is Ilock. It goes with index positions. That's why only integers can be used. And then disregard these labels. These are just labels. They are not positions. That's why 1 is referring to 3, this row. Disregard the 2 here. That's just a label. The index position don't change regardless of the label. So 1 through 4 is going to get you this row, that row, and this row. It's 1. The 0 row is left out. And if you do this, then the 0 row will be included. This is lock using row index labels, and the labels are using string values. All right. So and also one more critical difference. It is not going to leave out the ending label. This is one more critical. I guess there are 2 critical differences. With lock, it's inclusive. It includes the label 4. So you are going to get 4 rows here, interestingly, right? Because this makes sense if you think about it, because this is going by labels. It's not going by number sequences, right? So with labels, there's no beginning 0 trick, right? With indexes, there's a beginning 0. That's why the ending is not included. It stops right before the end perimeter. With lock, it's a different animal. It's not indexing. It's very different from the natural indexing in Python. It's all inclusive following that sequence. And there's more interesting points very soon. So here with lock slicing, you are going to get everything beginning with 1 and ending with 4. If you dare try the integer values with lock, you are going to get missing or an error because there's no such index label. Of course, you can use I, by which you'll get the same result as above, right? So with this, you get an error. Let me return the strings. Okay, that's good. So I hope that's understood. This is very critical. You probably will have to go through some getting used to before you completely get used to it. One more example. All right, the same thing. Okay, the same thing with the slight twist. So if you compare this df4, the row indexes labels, they are strings. This is 1, 2, 3, and 4. If I change it just slightly to 2, 1, 3, 4, all right, the orders are different slightly. The elements are the same. With labels, it doesn't follow the number sense, right? With labels, not with labels, or with the string labels, it is what it is. I guess the natural order is different from the meaning of the strings. So in this case, if I slice by lock, I slice from 2 to 4. Do I get 2, 3, 4? Or what do I get? I just tell you what I get. I get everything. It kind of doesn't make sense because 1 is not between 2 and 4. But here, the behavior of slicing using lock is you slice beginning with this label, ending with this label, and get everything in between. So it's not going to interpret the string meanings. It's only going to get everything in between. So whatever is in between is is gets sliced. Right? So with lock, you really cannot use the same formula to calculate number of elements that you return. Right? You cannot calculate. You cannot subtract 2 from 4 because it won't work. In this case, it's not going to make sense on the meaning, because Python cannot interpret the meaning of the letter of the strings. Strings are only intelligent animals can interpret, So, yeah. I think that's what and maybe one last point with DF4, let's use DF4. If you specify, if you index, let's say, the Ilock, in this case, use the index position 0. If I index with 1 row, I'm going to get a series. However, I said before, if I want to retain the structure, if I want to retain the dimensions, I want to make it, I want to inherit the data frame structure, but only get 1 row. What I can do is add another layer of brackets. I think this will work. In this case, I get another data frame. I get a data frame by slicing 1 row, but I keep it as a data frame. So it has 1 row and 3 columns and still is a data frame. It's different from a series. If I only use 1 level of brackets. So this behavior is the same with arrays. The only difference is that we use either ilock or lock. Okay, with data frames, let's see. I only have one more last point before I collect questions. All right. So previously I said so. Data frames or series use the ilock or .lock almost always. Almost always use .ilock or .lock because you are going to get unexpected results if you use bare brackets for with data frames or series. But there's an exception. Let me clear some of these to get some more rooms. Okay. So DF4, that's DF4. Okay. Now, when do I use bare brackets to index or slice? You can use bare brackets with data frames or series, but more likely it's going to be data frames. You use bare slices or bare brackets to slice or index only if you want to slice the entire column. So, with data analytics, we look at the rows and columns differently, right? It's like a spreadsheet. Think of data frames as a spreadsheet that has column names and row positions, but more than spreadsheets. Spreadsheets doesn't have row indexes. It follows natural numbers, but we also assign row labels. We can change them as well. So there's one more metadata elements, but it's very similar to spreadsheets. With spreadsheets, we know that we store the columns vertically So column labels in data analytics, they are variable names and they are meaningful, right? So typically we expect the values in the same column to be similar to each other. They represent the same meaning. So let's say age, the age column stores values about age. If it stores a year value, then it's an error. It's a mistake. It's a typo, or it's a input error. For an age variable, we only expect age. For a year or date of birth or year of birth column, we only expect the year, the 4-digit or sometimes 2-digit year indicator, right? So the columns make sense. I mean, the columns are especially meaningful. And then we interpret information from the columns based off even just the column name. So we typically don't use numbers to name the columns, but we use letters or names, meaningful names, to name the columns. That's why a lot of times in doing data analytics, we will need to refer to a specific column and do some, manipulations about it. Sometimes we look at the missing values of this age column, particularly because we want to use that column sometimes individually, or we need to, let's say, look at the distribution of age. So we name specific columns. So that's why there's a special use case of using Bauer brackets for data frames when you only index or slice the columns. So here's how. If I want to select column B, I don't have to use lock or Ilock, and then I can give the column label in and give the column label in the Bauer brackets and get the column. Now tell me there's a problem here. Tell me what the problem is. I'm going to get an error. What's the problem?
It's gonna be a string, so it's gonna be between quotation marks.
Yes, you need quotes, exactly. To slice column B, you need quotations, single or double, it doesn't matter. But you need quotations because it's literal strings. B without the quotes meaning it's a variable or it's an object that's defined, but it's not defined. So you need that. By doing this, you're getting a one-dimensional series object, right? Just as what we talked about with the Ilock or lock, or with array indexing, you get one-dimensional. And in this case, it's a series. Each column is a series. Even each row is a series, but we look at columns more often than look at rows. In order to get a data frame with only one column, you add another level of brackets, then you get one column data frame, right? That point is emphasized enough, I think. Okay. Let me remove one layer of brackets. So this gets a series. Now, how do I replicate the same slicing or indexing with Ilock? Let's say if I want to use Ilock, I don't want to use Bauer brackets. I want to use Ilock to get column B. How do I get that? In this case, that means I'm going to get all the rows of this column B, which happens to be in the position of 1 in terms of columns, right? So because the first dimension that you specify is always the rows, this notation is not going to give you this column, and we can try. you're going to get this row and disregard the label. You're going to get the row with index position 1. So you're going to get row 3, 3, 4, 5. And it becomes a series. So that's not what I want. I want this column B. So in order to do that, you have to specify that one index position 1 is on the column, which is the axis 1, the bottom dimension. And at the same time, I have to specify that I want everything with the rows, right? In this case, you're going to use the slicing, the special slicing, notation, which is 1 column. All right, with that notation, you're going to get the entire column. So this is the same if I run this. That's the same. So to replicate the bare brackets notation, you would have to specify the entire columns. Use all the rows by using the colon notation. All right, so these are all the, I would say, fundamental points and techniques with arrays and data frames as well as series, but these are not just fundamental, these are critical. They are very often used. They are so useful, and they involve perhaps the most frequent bugs of beginners programs, unfortunately, just because they are so often used. That is all. Now, time for quick break. As well as time for some questions. So I stopped the sharing. Now, do you have any questions? And questions that are related to the demonstrations I just did, so that, we can revisit very quickly if you have lingering questions or related. If not, after a short break, we're going to go through Hackshop 3 very quickly. Hackshop 3 is shorter. And then I'll talk about a few questions in homework 2, because that's due this week. Questions?
Professor, can we go back to broadcasting and can you brief some more about it?
Sure. Let me. All right. We don't have to go back because that's only one slide. But what we can do is create a few cells. Not here because, okay. Yeah. All right. So if the question is broadcasting, then let's do a few demonstrations. Specifically, and then what is your question about broadcasting?
I did not get how do we implement it, because there was
You got cut off because you muted.
yeah. So I was confused. There was a cell that said 06812. I did not understand how are we implementing this broadcasting thing.
Okay, so let's say maybe it's a good idea to make some joins. I think I talked about these. Okay. Anyway, so broadcasting. Let's use arrays to demonstrate because it works similar on data frames, but only up to 2-dimensional arrays. We're not going to do super complex multi-dimensional array broadcasting. That's unnecessary here. So let's say we have a array of assuming there are 4 elements here in each of these groups. What is the dimension here? is what by what. This is just to refresh the concept. What's the dimension here? Assuming this is an array. Anybody?
3 by 4.
3 by 4.
So yeah, 3 by 4.
3 by 4. Exactly. So let's say, all right, I don't have to fill in the numbers. Just know that there are 4 elements in each row. And broadcasting is when you do mathematical operations, typically mathematical operations of 2 arrays that has different shapes. Let's say if I plus another array, and I'm very quickly running out of space here. So let me do something here. Let me do this. That's neat. Okay. All right. I have more spaces to work with. Now, if I have another array, let's say one-dimensional array. Oh, I lost my pen. Okay, good. I have another array. Let's say also have 4 elements. If I add them together, it's going to try to broadcast because the shapes are obviously different. This is 1 by 4, or maybe 4 by 1, because with one-dimensional array, the shape is not always clear because it's just a vector, right? You can make either way. So it may be 1 by 4 or 4 by 1 depending on the context. Python is going to try to broadcast by adding this vector onto multiple items of the other direction of the other dimension, but then add the elements, add the content element by element in the matching dimension. So assuming this is 1 by 4 instead of 4 by 1, then the 4 is going to match with 4. So it will try to add this row of new row to the first row, and then to the second row, and then to the third row, in a sweeping format. But then on each of the row, when it adds, it will do element-wise adding. So that only, 1 is added to the first element, 2 is added to the second element, 3 and 4. So different numbers are being added onto different columns, but across the rows, you are going to have the same behavior on the same column position. I hope that makes sense. All right. If in the other case that you have the same first array, 3 by 4, and then you are adding a column, so 4 by 1. Let's say 1, 2, 3, 4. This is the same case or similar case as demonstrated previously in the demonstration. In this case, it's 4 by 1. Python is going to try to add this column into the first column, second column, so on and so forth, with different values added to the different rows. But the same value, +1, +1, same values added to the different columns, different values added to the different rows to broadcast. So hopefully this makes sense. It's hard to explain, but easier to just, make your own arrays and try a few things to understand the process. However, if none of these don't match, let's say if it's 5 or 5 by 1, it's not going to work. It will Python will try, but will stop working. Then it will complain. So that's broadcasting. Even if it's 3 is smaller than 4. So in a way, you can kind of broadcast in the irregular format, but no, it's going to complain. It has to match exactly the same. Hopefully that makes sense.
Yeah, I got it. Thank you.
All right, sure. Now, shall we take a short break? We will come back in, let's say, 5 minutes to do a few stretching. We'll come back at 7:47. And in the meantime, if you have questions, let me know. All right, welcome back. Now let's resume. So just a few more points. One last point on data frames. And sometimes it's useful to just get the values, the content of data frames as arrays without those metadata, without those index values and column labels. Just because you want to assign new labels, and you can use either of these methods. With a data frame, you can use. I think I'm sharing, right? Yes. Okay. With the data frame, you can use dot values, but without brackets or parentheses. This is getting the attributes values of the data frame. It only gets the NumPy array. An alternative method is to use a method to call the to_NumPy parentheses. This is a function, not attribute, but this is function. It's going to turn the data frame into an array without changing the original data frame, but turn it into an array and return the array values. So both of these will return exactly the same thing. For series, you can use toList, because with series it's lower dimensional. You can always use these, but also additionally you can return a list. Then you don't have to worry about arrays. Sometimes you only need a list. You don't need an array. But toList will not work on data frame because a list is one-dimensional, but data frame is two-dimensional. You'll see me using these functions or attributes in the tutorials. So whenever you see those, hooray. And I believe these points are talked about. With range, I also talked about the difference. Defining data frames with lists. This is using the, I think this is using the dictionary format with curly brackets. Then you can use lists to define different columns, different column objects of the data frame. This is demonstrated in the tutorial. An indexer, this is, I'll skip this now. It's going to, you'll get more practices in, I believe in the third homework, you'll get more practices here. This is indexing using an alternative method. This is using a Boolean, typically Boolean indexer, or maybe in homework 2. We'll see. If you have questions, let me know. This is defining an array of true or false, and then use that array to select relevant positions or relevant elements or relevant rows of a data frame or array. That's also related to filtering. You know, true means to retain that element. False means to skip that. We'll talk about more when we see the examples. Okay, so with that, we'll transition to Hackshop 3. Here is Hackshop 3. I'll quickly run through. By this point, I hope that most students have looked at the questions and started attempting the questions in the Hackshop. And let me make it bigger. And remember to follow the requirements. Rename your notebook to include your name and remove the symbols, smaller than and greater than symbols. fill in your first and last name. Run each cell, including the code cell and markdown cell. You have to run the code cell for the questions before you can use the objects. And don't forget to save your work. After you're done, save your work by saving explicitly. You don't have to download as notebook because after you close it safely, you can turn in the same notebook if you know your way. Otherwise, download as notebook, and it's going to be downloaded in the download folder, submit it to Blackboard. You don't have to zip it. You do not have to zip it. All right. The first questions is straightforward. You know, import two things and name and use appropriate alias. So NumPy and pandas. I'm just going to run this. Okay, we talked about this. Let me remove the stylus heads. Okay, how do you make an array by generating numbers from standard normal distribution? So this is going to be using the random function groups here, or object groups here. And inside the NumPy.random group, there are different specifications. There are different objects. With standard normal, you're going to use, not standard, sorry. Rand is random, but you have to use rand_n, which means normal. Standard normal distribution. If you only use rand, it's going to give you, it's going to generate values from a standard, from a uniform distribution between 0 and 1, and it's always going to be positive. So in this case, you have to use rand_n. And then as with array, yes?
Instead of np.random.r rand_n, what about if I use .normal? Can I use that as well?
I think, okay. I think so. I think so. But carefully check the result. Let's see. So if I use rand_n, that's a good question. If I use rand_n, I can specify the shape directly, I think, and then I don't have to reshape. And with this, I'm going to get an array of 2 by 5. And then let's do that. That's right. And confirm that there are 2 dimensions here by 2 levels of brackets with 5 elements each. And with this, with standard normal, with mean 0, the distribution has a mean 0, center 0, standard deviation of 1. You expect the values to be very close to 0, between -4 and +4. But it's going to be positive and negative equally likely. So, but is this complete? No, your answer is complete only if you assign it to the object and then you also print it. Okay, in that case, that works. So as to your question, Pervez, you asked the question, right?
Yes, yes.
Okay, let's try. If I use normal, 2 by 5. So this
when
is
I
what you
did
get.
that, I also defined size equal to and then bracket 2,
Sure.
5.
So right. So you can see the difference. Of course, if you can make it work, that also works. But you can clearly see
so after normal,
rand_n is better.
So after
in this
normal,
case.
the bracket and then size equal to 2, 5. So that's what I did.
So all right, sure. What I suggest is you use this one as your preferred method.
Okay.
And then any additional method will be your additional tools.
Okay,
That makes
thank you.
sense, right?
Thanks. Yeah,
I'm not
thank
going
you.
to demonstrate this method here. So, but know that for other students, don't include this cell. This is not to show correct answer. This is to try a few things. All right, great, good question. All right, next, with the myArray1 to replace value. So this is to show that, or to demonstrate that you can put the indexing notation on the left side of the equal sign and then assign value to it directly. So which means it creates a view which lets you access the actual memory in the computer, right? And another point here is with the index position always starts from 0. So the first row means index 0. So you always have to translate that. So very quickly, with arrays, you use bare brackets, right? With 2 dimensions, you need to have a comma in between. First row, second element, 0 and 1, and replace with numpy.nan. And there are several ways to do that. You can do this, you can do this, you can do this. All leads to the same result, right? So, and then the second replacement is second row, meaning index position 1. Fourth element is 3, always minus 1. Okay, after these, I'm going to print it. You can see 2 missing values. Confirm is first row and then second row and fourth. All right, no problem.
Can I again ask a quick question?
Sure.
So,
yes.
in my case, but I did like myArray_1 and then bracket and then the curly bracket 0, 1 and then comma and then 1, 3. And then I did equal to and dot. So I can use just in a single row instead of 2 different rows. That will make sense to you?
You use curly brackets.
No, small bracket. That's what I meant.
Okay, you use curly brackets like this.
No, sorry, the regular bracket is
I see convention
regular brackets like this.
no, initially the square bracket and then this bracket inside it. Yeah, so now.
And then this.
Yes, and then I did.
And then
0, 1.
But why?
And then
you see my point? Why the
after
additional?
Bracket, comma after this bracket. And comma, just comma.
Just comma.
Yeah. And then again, this bracket, and then I put 1, 3.
Okay.
And
so
then equal to
is...
np.nan. So that's
how I see. So you use fancy indexing.
Okay. I was just curious, like it's like
and in this case you can lose the bracket. No, I mean no, you have to have some kind of bracket, but you can also do this as well. So in this case, it's going to give me the 2, since the values are replaced, it's going to give me 2 missing values. This is what we call fancy indexing.
Okay.
Interestingly, I was saying that there are literally little or no use cases that you can that for you to use fancy brackets, but in this case, for this problem, it works pretty well. So great. Yeah.
Okay.
Yeah. So in this case, you only need 1 line.
I was just curious. I wanted to confirm whether what I was doing is correct or not. So thank you.
Yeah, clearly that your approach works and it has its name. Very well. Thank you. Good question. All right. So so let's see. Either approach will work. Okay. All right. Let's go to the next one. Make another array using the identical shape. So this you can do it in a few different ways. You can either get the shape or dimension of the previous array and then assign it to or make use of those shape variable to define the new array, or you can hard code, which sounds like a bad word. You can hard code by specifying the shape, which is 2 by 5. So you can give the 2 by 5, or you can give the 10, right? 2 by 5 is 10. You can give the value of 10 and reshape to 2 by 5. That's considered hard coding, but it's fine here because it's simple exercises, right? So the ideal way, by which I don't mean you have to use this way, but the ideal way would be to define two things, shape 0 and shape 1, which means the two sizes for the two axes, the two index levels, is my array 1 dash shape. So what it does is unpacking. The my array 1 dash shape will get a tuple. It's like a list. We'll get two things, and I assign it to two things. Then each of these becomes an index, and we can see. I'm going to print out a tuple, and each is represented by one of these objects. So shape 0 maps with 2, shape 1 maps with 5. And with these, I can define my array 2 as, first of all, let's make a sequence. So NumPy A range, make a sequence. I can do 10. Of course, I know 10, but since I have the two shapes, what I can do is to calculate the total number of objects here. And then copy this, and then I will make it into a particular shape like that. So then in this case, I'm going to get a two-dimensional array with the number sequences. And finally, print it like that. Right, so alternatively, of course, you can do like this, because it's a simple exercise and you know the numbers. All right, so both will work and both are fine.
Professor, can I also use the array function?
Array function?
Yeah, np.array and then range within that?
And range within array.
No, np.array and then within the brackets, I use range.
Yeah, that's what I said, range within array.
Yeah.
So yeah, so this is a good question. Great. It will give you the same result. Of course, you have tried. I mean, so in a way, NumPy A range is invented to complete the two tasks in one shot.
Oh, okay.
So you see what it means. So, of course, NumPy A range would be preferred because it's, calling one thing does two, but fundamentally there's no difference.
Okay, thank you.
Yeah. So it's good to know, a sort of a more efficient function, but this is no problem. All right, great. And cast the type. All right, so it calls a different method. Since my array 2 is integer type, to convert it to floating point, you will simply, and I think there's let me return to the previous page. It says make sure the data type is integer. By default, a range will give integer. Let's see if range gives the same thing. range also gives, and if you make it an array by using range, it gives, of course, you need to reshape, but it also gives the integers. Okay, so something I talked about earlier, that when you fill in values into different positions of an array, the bottom position, which is in this case, if we were to, so there are two index levels. The bottom level is the columns. The column index level changes more quickly, which means when I reshape the values, I'm filling in the number sequence into the 2x5 positions. By having the columns flipping more quickly, in the first row, after filling in 0, it flips to the next column, instead of flipping to the next row. So it fills the entire row by going through all the columns first, by changing the columns, before it changes the row number to fill in the next row. That's what I mean. By default, this is the behavior of Python. But there's an option that you can change it. You can fill in the columns first, instead of filling the rows first. But we'll just stick to the default and just know this interesting fact. All right, casting type we will call the as type function, and then simply give float. And you can use this named type, or you can use the name, the literal name will give you the same thing. But keep in mind here, it's asking you to cast the type, which means to convert the type, and you need to replace the values of the original arrays. Otherwise, if you call this, it's not going to affect the values inside the array. The array2 remains the same, and if you call the type of the original array, it remains integer. So what you need to do here is to assign back. Don't forget this part. So assign it back and take a look at the value, and then check the value. It becomes float, and it's permanently changed. All right, so keep in mind. Appending, okay, concatenating. Now the
Excuse me,
preferred
Professor.
method, yes,
Can you go back to question 5?
yeah,
Okay, I just wanted to see, you put float in quotation mark, and it's fine
Yeah.
if I don't put it in quotation mark, right?
yes, it's fine.
Okay,
It's two alternative methods, totally fine.
thank you.
Sure. All right, with the with appending, there are two alternative methods. Here, the point is to practice concatenate. Concatenate can do both, as you know, but then concatenate would require to specify the axis. It won't assume, or maybe it will assume, but the default behavior is to append. In this course, we make a difference between appending and joining, or we call SQL join. In the sense of concatenating two data frames. If we say append, it means to stack the rows in a vertical direction. And if we say joining, like SQL style join, then we're putting columns of one data frame to the columns of another data frame. So side by side, so that's the difference. But concat, NumPy concat can do both. in this case, let's see, let me check my notes. In this case, we call the NumPy because so far it's all NumPy arrays. NumPy done concatenate. And then you need to put the two arrays. Okay, but there is a problem here. Can anybody tell me what the problem is?
You need to define myArray3.
No, we only have myArray2. Oh, no, right. That's a problem. But before we get to that, we have to assign it to the new name. But before we get there, there's another problem.
We haven't.
It's missing the brackets. Like we will need to.
It says only integer scalar arrays can be converted.
So interesting. So Anam is right, I think. Anam is on and Arasli, hopefully I did butcher your name. Arasli. The error type is telling something that doesn't make sense. Does that mean I have to provide an integer? Only integer scalar arrays can be converted to a scalar index. What does that mean? I'm not trying to do a scalar index, or I'm not trying to provide a scalar. I'm trying to append or concatenate two arrays or multiple arrays. I can do 3 or 4 or 5. That's fine. But it's giving me this error. This is when debugging with the error message don't help too much. But not always. It's not always like that. Sometimes error message is very helpful, but sometimes error message doesn't help because you know the Python machine doesn't really anticipate what you're trying to do, or doesn't really assume that you know enough about the function. So really, what's missing here is a list formation, and Anam said it right. You need a square bracket in here. Why? Without square bracket, what does it mean? I'm providing two parameters, where the first parameter for this function should be the entirety of the data objects. It should be a list of different arrays to be put together. Only in the first parameter. With the comma, it is indicating that I'm providing a second parameter to specify how to concatenate. But without the bracket, it looks fine, right? So this is where debugging becomes very difficult for beginners. This is, you know, you can only grow by accumulating these experiences. So using a pair of brackets would put these two together as only one thing. The comma is inside the list formation. So this is a list of two data objects, and then the specification is correct in this time. And now I need to specify, you don't have to, but this is just to illustrate. This comma indicates that there is a second parameter to provide to this function, and this is x is 0. Now, I'll talk about that in a little bit. So this is what it really refers to, the error type. Only integer scalar. I need to provide integer scalar. And if I provide arrays, it has to be integer arrays, integer scalar arrays. But here in this case, I'm only providing an integer that works. It's a scalar as index. So I'm specifying that. So you need to provide a list formation for the arrays. Okay, so I'll talk about this in a little bit. For now, I'll remove that because that's a default setting. By default, it concatenate the arrays according to x is 0. So let me remove that and run this. It works. The first array 2 by 5 is on the top, confirming 2 dimensions, and the second array is on the bottom. So it's stacking, it's appending according to x is 0. So as I think Parvez said, you would have to assign it to array 3. That's right. So once you do that, you can print my array to confirm. All right, back to the point. If I concatenate by specifying axes, this produces the same result. But if I change the axis to 1, it's going to, this is where it becomes tricky. If I specify axis is 1, it's going to do side by side, and then the resulting shape should be 2 by 10. And then, although it looks the same, but really it's different. This is a long row with 10 columns without breaking. So it's only one dimension of this entire string. And the array on the right is these 5 objects, which was at the bottom if you append the other way, right? So this shows the axis. I don't know if you guys have questions about how this axis is understood, but I'll just provide a few quick tips using the slides. So let's use 2 arrays to demonstrate. So I have one array, 2-dimensional array. It's 2 by 5. Okay, and then I have another array. Same thing.
Professor? Oh,
Yes.
never mind. Sorry.
Yeah, you can see the slides, right?
Yes, I can now.
Okay. So 2 arrays. If I use concatenate, so assuming this is concatenate, I'm using my mouse, so it's not very easy to write. But so if I specify these 2 arrays, but then I say axis is 0. What does it mean? 0 is the row index. So by specifying axis equals 0, it's doing the concatenation in this direction, which is the row index, the higher level, right? In this direction, meaning the first array and the second array, that's stacking, that's appending. However, if I say axis equal 1, it's going to do this direction, which is the column label, column direction. So in this case, it's going to stack side by side. All right, hopefully that makes sense. For almost every use cases, when you specify axis equals 0 or 1, use this logic. It should make sense. At least to me, it makes sense every time. All right. So that's 6. For calculating column means, all right, yeah, another use case where what I just talked about, the axis will work. So if it's column means, let's go back to here. Column meaning I'm calculating the means of these one-dimensional arrays, one by one. So in the end, I get 5 elements, right? So it's doing column means in this direction. And if it's this direction, then I'm specifying axis is 0 because it's vertical, right? It's column means. So my array 3 specifying axis is 0 will give me 5 things. Now, the tricky part here is there are no values because we replace the no values here. And for NumPy array, when it's calculating aggregate values of an entire dimension, whenever it meets the missing value, it's going to result in missing. So it's fine that you have 2 missing values. I know that some of you might have searched to how to ignore missing values in calculating means by specifying some of the options here, but it's entirely not necessary. And here's why. What if I convert the array to DataFrame? And take a look. If I convert it to DataFrame, it's going to be like this with metadata and still with the missing values. And with the DataFrame, I'm going to call the same mean function and then the same axis, you know, in this direction. So calculating column means I will get 5 values. And in this case, I'm going to get a series. But regardless, let me get rid of the metadata by using values we talked about, or we can use toList or toNumPy. I'm going to get an array. In this case, I'm going to get real values for the means. In this case, the data frame is going to, by default, ignore the mean values elements and calculate the mean of the remaining non-missing data values. So you can compare that without the missing value elements, you get the same mean. With that, data frame is kind of more superior, or more convenient. That's why in data analytics, we almost always, at least in the data preparation stage or data cleaning stage, we almost always use the data frame as much as possible until the point that we have to train models. We have to get rid of the metadata because those will interfere with calculations. Matrix calculations means a lot in training the models, but in doing data cleaning or data management or data manipulation, it's much more convenient and much more intuitive to use data frames objects rather than arrays. Next question is calculating row means. Row means is doing this direction, right? This direction is axis equal 1. So by change of that one value, you get a different array. In this case, you also have 2 missing values. Yeah, you have 2 missing values as well, but 4 objects in total. So I'm going to skip here. This is the last question. It's a conceptual question, and you can get these off the textbook readings. So I'm going to mostly skip it here. And hooray, you finished. Very well. Any other questions about Hackshot 3?
I have a question, Professor.
Yes? No?
Is np.nan the same as none? Is there any difference?
Can you repeat the question?
The np.nan n. Is it the
That's
same as
NumPy dot
the
NaN.
NumPy non missing value? Is it the same as specifying like just none, NA and E, just the word none?
That's a good question. I don't believe they are the same.
They are different.
Logically, they are different. Yes.
Yeah, all right.
Right. They're different. Right, because if you evaluate none, N-O-N-E, from Python, it's going to evaluate as false, I think. But missing values, it's going to evaluate as true. I tend to believe that, but most likely there's no use cases that where you will be confused about these two. You know, so NumPy none is strictly in a array format. And then within that context, you would not need to use none, the Python none Sentinel in any case. I don't believe so. So those two will not interfere.
Thank you, Professor.
Sure. Any other questions? If not, we'll go to the last item, the homework 2. So let me share. Homework 2. Make it bigger. Make it very big here. Maybe too big. Okay, I'm going to talk about a few of these. Some of these are very similar to the hackshop questions. So consider these as additional practices with slightly more complexity. So the structures are slightly more complex. You even have 3-dimensional arrays here, but follow the same logic and debug or evaluate your results carefully. All right. I'll highlight some of these questions, the debug questions. For here, the first debug question, question 3, seems to only have problem with the data type. With the data type, int32 is not a well-defined object, but it is. So that's why you have this classic error, name error. The name is not defined because it's not known. It's only known within context. The int32 is a sub-object as a NumPy data type objects. So you would have to call the NumPy dot. And also, I don't think you can use this too because the literal format is not identified. But by removing 32, by referring to literal int, it should work. But that would become different from the additional intention, the original intention. So the original intention is to use NumPy the int32. All right, that one is, I guess, just about that. But the other two debugging questions are slightly more interesting. So here, this question tries to calculate the difference element-wise between two arrays. But there are two problems. First, you cannot subtract numbers from strings. It just simply won't work. Not even when you have two string lists, it won't work, or string arrays, it won't work. Only when both arrays are numbers, then that can work. And also, even if you cast the types to numbers, the results are not as intended. 101 minus 0 is still 101. So the result, the intent seems to be to subtract odd numbers, only odd numbers from the first array. So the sequence, the number sequence is not constructed very well. So there are two changes that you would need to make to debug this program to cast the type into integer or floating number is both fine. And also to reconstruct or to modify the A range specification here to only get odd numbers. And to do that, you would need to specify different steps and also with different starting points. Hopefully that makes sense. And with the last debug question, the problem is that with arrays, the plus changes the function here. With arrays, the plus operand would mean element-wise addition, different from lists. For lists, the plus sign means to concatenate the list. So somehow this program is trying to concatenate two lists, but they end up to be arrays. So what you can do is to make them lists. I talk about how to do that. Well, anyway, you can get lists by using toList, toList, I believe, using arrays, toList. Let me run this before I can do any demonstration. And okay, here. So if I have the two, so by running this, both arrays are defined. If I call array31.toList, I get a list. So what you want to do is to get the list from two arrays and then follow the rest. And then you can concatenate them together. Or that's approach one. Alternatively, we just learned how to concatenate the arrays, right? You can first using arrays to concatenate and then make them. So in that case, you don't need these. You replace this line with concatenation and then somehow to only get the list of the concatenated array. So here is method 2. NumPy that concatenate array 31, array 32, but remember to put them in a list. And then by default, it's going to stack the other way. Let's say it's going to stack. It works. It still works, even though, yeah, maybe because it's a one-dimensional array. It always just put them together. Okay, so this works. After you concatenate, you can just extract the list, and that would be the same format as this one, as the desired answer. Okay, so that's the 3 debug questions, and 2 more questions.
Professor?
Yes.
Professor, can we just use tuple for this question?
What do you mean use tuple? How do you use tuple?
If we change np.array to tuple for both the list and then run the codes as is, the results are the same.
I see. So let's see. So what you mean is to simply remove this.
Yeah, and use tuple.
That's what you mean.
Yep.
Yeah, of course. So these are, I mean, technically these are not an array then, but that would be, I mean, you see the point. It's different, I mean, different styles of resolving the issues. But you can see that the intention is for you to understand how to, once you so given arrays, how do you convert them into lists? So that's the original intent. But of course, to fix the errors per se, there are multiple ways to do that. For me, for the grading purpose, I wouldn't be much as picky, as long as the bugs are resolved. All right, so this works. Yes. Is that good? I don't recall who asked the question, but are we good?
Yeah.
Okay, great. Enough. Two more questions, and these calculating well, I guess let's see. Calculations, element-wise calculations should be mostly fine. Calculating aggregate numbers, aggregate values like sums and means should be all fine. Use the appropriate axis values. I want to talk about question 15. Okay, this is about choosing the right method for indexing. So for grading purposes, as long as you slice the correct elements, it's all fine. But in terms of efficiency, it makes a difference of which one you choose. If the purpose is telling you the positions, the third and fourth, that's the positions, right? That's the positions you can translate into Ilock more easily. The third would be position 2. The fourth would be position 3. So you can either do a slice, you can do indexing with lists, or you can do slicing, would be better. 2:4 would be slicing third and fourth rows. And then in terms of columns, it's also giving you the index position. So using Ilock would be ideal for question 1. But for question 2, it's giving me the index labels. Label 2 and 5, be sure it's strings, but only the column with label 1. And this label 1 is integer. Be sure to note that. Right? Let's take a look at slice the data frame. My df1. Okay, it's in the previous, and you can only get those by completing these. What? No, not these. By completing this question correctly. Okay. Anyway, so Ilock will be the ideal method for the first, and lock would be the ideal method for the second part of the question. All right. One last point. One last point is question 18. I'm not sure how many have looked at it, but let me just say, and then you can rewind. You can replay the video afterwards. So the purpose here is to hopefully make it clear that with empirical data values, sometimes it goes against what theory would tell you. So this is about random number generators, which is supposed to generate numbers entirely randomly. However, the random number generators are not perfect. They generate numbers based on pseudo random algorithms. They are not completely random. That's the first point. Second point, random numbers are supposed to not have any correlations. That's why they are called random, right? They are independent. The first number is independent from the second number, even if they seem to be having some relationship. If the first number generated is -1, the second number is 2, the third number -3, the fourth number +4. Based on these four numbers, -1, 2, -3, 4. It seems to follow some kind of pattern, but if I tell you these numbers are generated purely randomly, like these four numbers, you know, it's hard to believe, but you know, just say that these numbers are generated randomly, then there is no theoretical relationship between these numbers, although it looks like it's following some kind of pattern. You know, it's oscillating value 0 and then widening with the steps. So this tells you the second observation, that in empirical data, what seems like strong correlation doesn't have to be real correlation. So you have spurious correlation, large correlations by chance. And this is mostly because the numbers are very few. If I keep going and I get this, and now you start to see no pattern at all, even though the first four numbers happen to be following very strong patterns. So with more values generated from random number generators, the seemingly strong correlation or patterns will disappear as you incorporate more numbers that's generated from the same generator. So this is the point of this question. Now, conceptually, it asks you to make 3 data frames or arrays. All of the 3 will have 3 columns, but they will have different number of rows. So the 3 columns, think of them as 3 variables. We say, you know, in spreadsheets, we say each column is a variable. The first data set has 3 variables, but 10 rows, which means 10 observations. The second data frame has 100 observations. The third has 10,000 observations. With very few values, let's say 10 values in the first data frame of each column, if you look at the correlations between the 3 columns, you are likely going to get fairly sizable correlations, even though these numbers are generated randomly, meaning they should be theoretically independent. However, they turn out to be strongly correlated at some level. So this is the small number chances that goes against theory. However, there's a fix. The fix is keep generating more numbers and the correlation will dissipate. The correlation will disappear. So let's do some quick demonstration. The reason I'm asking for data frame is that once you have the data frame, it's very easy to calculate correlations as versus arrays. Of course, I can generate arrays, right? It's based on arrays, but to calculate correlations between the columns using data frame is easier because it has correlation methods. So the way you generate random numbers is the same, 10 by 3 in this case, right? And then once I have that, I do correlation, and then let's round the decimals to 3. And then I can simply copy and then change one parameter only. Make sure it's 10,000, not 1,000. Okay, so let's quickly run these. Run this. This is a correlation. Run this. And run this. Same correlation tables. And on every table, you only look at one diagonal part. The upper diagonal or lower diagonal, it's the same. It's symmetric if you cross-match off the diagonals. And then ignore the diagonal line because its correlation with itself is always 1. So I'm going to look at lower diagonal portion. With only 10 values in each variable, I get correlation of 0.5, even though these numbers are randomly generated. How? It's just by chance, right? The previous example I typed, -1, 2, -3, and 4. It's strongly patterned. This seems like the same, same coincidence as well, but this is only coincidence. When you generate more numbers, the absolute number, the absolute size of the correlation, the largest one, reduces to 0.2 only by chance. And when you generate 10,000, the largest one is only 0.01. So this is as if you have a limit, function. Let me try to write something here, which will be the last point I'm going to write. Okay. So here. So with the random number generator, it's as if you have this theory. The limit of rho is the correlation of randomly generated columns, and n is the number of rows. As n goes from small to infinite, the limit of rho will approach 0. That's why when you increase the number of rows, the correlation size will be smaller and smaller, and ultimately it will become 0. Or to be more precise, it's the absolute value of rho will approach 0. So this is the purpose of this problem. For part 4, try to recap what I just said. With small samples, you get spurious correlations, even though the numbers are by theory, or in theory, independent. But as you increase the sample sizes, the empirical correlations will more approach and map the theoretical values of the underlying correlation. So that's the point. All right, that's all I intend to say. It's almost 3 hours. Wow. Right on time. All right, I'll be here if you have any questions. Otherwise, have a nice, enjoy the rest. I will keep recording for a few more minutes in case there are questions. But if not, enjoy the rest of the night. I'll see you in 2 weeks, I think. All right, if there's no more questions, I'll see you next time. Bye.
Thank you, Professor.
Yep.
Thank you. Goodbye.
Bye.
Thank you, Professor.
Okay, I need to stop the recording.